Hey guys, so today I'm going to be making a video on multi-dimensional kinematics. And the reason why I'm making video 2 after video 3 is actually because I thought I already made this video, but apparently not, so yeah. And if you haven't seen video 1, which is on 1D kinematics, I advise you to check that out first, unless you already know 1D kinematics. And without further ado, let's go over the 3 kinematic equations. So first we have that velocity is the initial velocity plus acceleration times time. The second one is that position is just the initial position plus the initial velocity times time plus 1/2 times the acceleration times t squared. And finally, the last one is that the velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. And this can also be written as x minus x naught. And it's important to remember that all three of these only work if we have constant acceleration. So if the acceleration is changing, you would have to resort to calculus, which says that velocity is basically just a change in position with respect to time, and acceleration is just a change in velocity with respect to time. And yeah, so that's basically what I went over in my last video. And for multidimensional kinematics, basically all these equations apply not only for the x direction, but also for the y direction, the z direction, and so on. And so today we're going to be looking at problems which involve multidimensional kinematics, namely trajectory motion. So for projectile motion, it's kind of self-explanatory. These types of problems are problems where you just have a projectile which is usually launched from the ground at a certain angle with a certain initial velocity, and then you have to find out things like the maximum height or maybe the total range. And some things to remember for projectile motion. So I'll spread it out. Projectile motion. Assuming that air resistance is negligible, we know that there is no acceleration or deceleration, and well, deceleration is just acceleration, but it's in the opposite direction of motion. But the acceleration would be zero. However, because of gravity, in the y direction or in the vertical direction, it's negative g. And yeah, so that's the basic overview for projectile motion. Also, so if we look at the second kinematic equation, I believe, which says that the position, terribly written, but the position is equal to the initial position plus, I said v naught t plus 1/2 at squared. Well, in this case, if we're looking at the x direction, this would be v sub x naught. So that would be the initial component, or the initial speed in the x direction, which is actually just using basic trigonometry, v naught cosine theta. And same thing for v sub y naught, which is just v naught sine theta. And usually in these types of problems, to make it as easy as possible, we would set the initial position as our origin. So the x naught would be 0, and y naught would also be 0. Also, keep in mind, because there's no acceleration in the x direction, we could write position for a projectile motion problem as just Vx naught t, or if you prefer, V naught cosine theta t. And then for the y direction, there would still be acceleration, but the initial position, as I said earlier, would be set as 0, so it would be v y naught, or v naught sine theta t minus 1 half g t squared. And keep in mind that for this formula here, this only works if we have level ground. Like if you're dropping something from a cliff, then we would have to have an initial y position that is not 0. Or even if we did set it 0, then the final y position would have to be negative. So yeah, this only really works in level ground. Otherwise, you're gonna have to make some sort of adjustments. Okay, so with that being said, I won't get into derivation, but actually, you know, what, I'm gonna do some practice problems. Yeah. And actually, before I do practice problems, there are a few more types of motion I'd like to talk about. So now we're gonna talk about motion on an inclined plane. So let's say we have a plane with angle theta, and it's like a ramp, it's 90 degrees, and we have some sort of object on the plane. Well, if we look at the force acting on the object, we know that there should be gravity here. Actually, let's not look at the force. Let's look at the acceleration. So we know that there should be, if there weren't a ramp here, it would be accelerating downwards at g. However, we also have to look at the components of this acceleration that are perpendicular and parallel to the slope of the ramp. So this is the perpendicular component, this is the parallel component, and with some geometry we can actually prove this, but this triangle here is actually similar to this large triangle here, which means that this angle here should be theta, which means that this component, which is perpendicular, is g cosine theta, and this parallel component is g sine theta, which means that this object would have to be accelerating downwards at g sine theta, assuming that friction is negligible. And this actually makes sense, because if theta was, say, 90 degrees, then, well, the ramp would just have the block falling straight down, and g sine 90 would just be g. And the other limiting case would be if theta was 0 degrees, in which case the block wouldn't be falling at all. It would just be like horizontal. And that would be g sine 0, which is just 0. And I actually did touch on this in my first video, but there's also centripetal acceleration. And this is basically when an object is accelerating, but its speed is staying the same. And you might be wondering, how is that possible? Well, acceleration is the change or instantaneous rate at which velocity changes, or in other words, the time derivative of velocity. And you have to remember that velocity is not just speed, it's speed and direction. So speed is just the magnitude of the velocity. Which means then that an acceleration does not necessarily mean a change in speed. It could also be a change in direction. And we see that in like uniform circular motion. If an object is going at constant speed in a circle, it's still accelerating towards the center because it's changing direction. And velocity is direction in addition to speed. And that acceleration is known as centripetal acceleration. And this is the formula. It's the square of the speed over the radius. Okay. And also, one thing I would like to add is that if the object is indeed speeding up and it's still moving in like a path where it turns, then it would actually have two components of its acceleration. So first, it would still have the radial component or centripetal component, but it would also now have a tangential component since its speed is changing. And tangential component would just be the derivative of the speed with respect to time. So yeah, that's important to know. Okay, let's see. Okay, so now it's time for some practice problems. Okay, problem number one. A bullet is fired horizontally from a gun and another bullet is simultaneously dropped from the same height. Which bullet hits the ground first? Ignore air resistance, the curvature of the earth, etc. And the choices are A, the fired bullet, B, the dropped bullet, or C, they hit the ground at the same time, and it has to be C. And the reason for that is, so if we look at the two bullets, we have the fired bullet and we have the dropped bullet. And since we want to know when they hit the ground, we don't really care about the horizontal motion. Which means that it doesn't matter that the bullet's fired, because it's still going to be accelerating downwards at g. So for both of these, the equation for their vertical position would still be the same. It would still be whatever their initial height is, minus 1/2 g t squared. And so they would have to fall to the ground at the same time if they're released from the same height, which the problem specified is indeed the case. Okay, next problem. This one's a bit more tricky, but let's see. A projectile is fired at an angle theta with respect to level ground. Is there a point in the motion where the velocity is perpendicular to the acceleration? So let's draw this out. So it moves in a sort of parabolic way and fired at angle theta. And the velocity is always tangent to its motion. Yeah, okay. So the acceleration is always downwards because, as I said earlier, there's nothing opposing the horizontal motion because we assume that air resistance is negligible, which means then for it to be perpendicular, for the velocity to be perpendicular to the acceleration, it would have to be perfectly horizontal. It could either be this way or it could be this way. But since the projectile moves to the right, or for the sake of the diagram, we're saying it moves to the right, we know it has to move this way at the point where it's perpendicular to the acceleration. And the velocity vector would always be tangent to the path, which means the only place where it would be horizontal is right over here, the middle point, when it reaches its maximum height and goes down. Sorry about that. And yeah, so here is where it would indeed be perpendicular. And we can also think of this in terms of the components of velocity. So here we can see that the height of the projectile is increasing. And we know that velocity is just a change in position with respect to time. And the same applies for the components. So if the height is increasing, we know then that it has a positive velocity in the y direction. But here at this middle point, we know that the height is neither increasing or decreasing. It's like perfectly still in the y direction here. And then after that point, it starts decreasing. Which means here we know that Vy is 0, which means there's no y component to the velocity, so it has to be horizontal, since there's only an x component. And so to answer the question, yes, there is a point where the velocity is perpendicular to the acceleration. Okay, next problem. A projectile is fired at angle theta with respect to level ground. Does there exist a theta such that the maximum height attained equals the total horizontal distance traveled? That is a good question. So, and actually, what we can do is we can try finding equations for the maximum height attained and the total horizontal distance traveled, and then we can see if there's data for that. So first, let's look at the formula for, or the kinematic equation for the y position. So we said it was, as a function of time, it was, okay, so we assume that the initial y position is 0 is v y naught minus 1 half gt squared, which can be written as v naught sine theta. Oh wait, there's a t here, okay. V naught sine theta t minus 1 half g t squared. And yeah, okay, so this is the formula or the kinematic equation for the vertical position. And so we first want to try to derive a formula for the maximum height. And we know at the maximum height, as I said earlier, that the velocity is 0. And using the first kinematic equation, we can find the formula for the vertical velocity, which is just equal to the initial velocity minus g times t, and this can then be written as v naught sine theta minus gt, and we have to set this equal to 0. So we get that t is equal to v naught sine theta over g. And all we have to do now is plug it in back into this equation here to find the maximum height. So max height is equal to, so the first term would just be v naught squared sine squared theta over g minus 1 half g v naught squared sine squared theta over g squared. And this whole thing would just be equal to v naught squared sine squared theta over 2g, which is half of this. So we eventually end up with v naught, okay, that was a brain part. Okay, v naught squared sine squared theta over 2g. And yeah, so this is the formula for max height. And now we can also find the formula for total horizontal distance traveled. And we know that when it travels its full range, and if we assume level ground, which is what the problem specified, then we know that there has to be okay, so dang it, lost my train of thought. Oh yeah, so we know that here the y position must be, or the vertical position or height or whatever is 0 when it completes its full range of motion. So now we can say then that y of t is equal to v naught sine theta t minus 1 half gt squared, which is equal to 0. And so if we try solving for t, we already know one of the solutions is t is equal to 0 because that's where it starts off. But we can also say v naught sine theta is equal to 1 half gt. T is equal to 2 v naught sine theta over g. So then now we can use this to find the total horizontal distance traveled. we have x of t is now equal to v naught cosine theta times t, and there's no acceleration, so we just leave it like this. If we plug this in for t, we get 2 v naught sine theta cosine theta over g, and using one of the trig identities, this can be further simplified to v naught sine 2 theta over g. Great, okay, so this is the formula for max height, and this is the formula for total horizontal range. So to see if there's a theta which could work, we just have to set these two equal to each other. So first we have v naught squared sine squared theta over 2g is equal to v naught sine 2 theta over g. Actually, you know what? I think it would actually be easier to change this back to this. So let's actually do that. So 2 v naught sine theta cosine theta over g. And so right away we can see that we can cancel out this v naught. And then this becomes v naught. We can cancel out 1 sine theta. And this becomes sine theta. And we can cancel out g. So this becomes 2. And we get cosine theta is equal to 1/2 v naught sine theta, which means 1 is equal to 1/2 v naught tan theta, and so theta would just be the arctangent of 2 over v naught. Okay, and then I run out of space. Oh wait, never mind. Okay, so this is what theta would have to be for the maximum height to equal the total horizontal range. And yeah, so we can say that it is indeed possible as long as v naught is not 0. Which, wait, actually, yeah, okay, so, yeah, so for any data which fulfills this condition, then yes. So the answer to the question would be yes. Okay, next question. Is the following reasoning correct? If the launch angle theta of a projectile is increased while keeping v naught the same, then the initial v sub y velocity component increases, so the time in the air increases, so the total horizontal distance traveled increases. Well, okay, that is actually clearly wrong because, so let's say you shoot it straight up, like at 90 degrees, and it falls straight down. Well, the total horizontal distance would obviously not increase, even though theta is at basically its maximum. And so we can see that the answer to that is no. I mean, we could derive it mathematically if we wanted to, but just thinking about it is, we can easily see that that's not right. Okay. A ball is thrown at angle theta with speed v naught. A second ball is simultaneously thrown straight upwards from a point on the ground directly below top of the first ball's parabolic motion. How fast should the second ball be thrown if you wanted to collide with the first ball? That is... Okay, actually, let me just draw it out so it's easier to visualize. So we have our first ball, and then we have another ball which is thrown like this. And imagine it goes upwards and downwards. It's kind of hard to see, but I'm trying to make it so that I can show that it's like straight up. Anyways, so okay, yeah. So for the first ball to collide with the second ball, they obviously have to have the same position at a certain time. And so if we actually let me reread the poem. Second ball is simultaneously thrown straight upwards from the point directly below the top of the first ball's parabolic motion. How fast should the second ball be thrown if you wanted to collide with the first ball? Okay, so first let's look at the equations for the first ball. So let's look at the vertical position. So, okay, yeah, so first ball, the problem specified it had some initial vertical velocity, which we'll call v naught sine theta. And let's call this point here the origin, just to make things simpler. So we have v naught sine theta t minus 1 half gt squared. And actually, let's call this y sub 1 t to avoid confusion. So this is y2 of t. And is just this is just v naught t minus 1 half gt squared. Because the entire velocity is in the vertical direction, so we don't really have to worry about any components. Okay. And if we look at the horizontal motion, so we have that this is just, okay, so looking at the first ball that's thrown, this would just be v naught cosine theta times t. And if we look at the second ball thrown, well, since its initial velocity only has a vertical component, we know that its position, or its horizontal position, has to stay the same. And since it's halfway for the total trajectory of the motion of the first ball, let's look at the equation that we derived earlier for the total horizontal range that the first ball would travel, which is, okay, so it's g naught sine 2 theta over g, which means then that this would be equal to v naught sine 2 theta, and that would be over 2g, which we could then write as v naught sine theta cosine theta over g using the trig identity. And we have to, and since we're looking for when it collides, we know that these two have to be the same. And for these two to be the same, we can see that t has to be v naught sine theta over g. And now we also want for them to collide, they have to be at both the same horizontal and vertical positions. Which means if we plug t in here, well, actually, we don't have to plug t in here because earlier we already derived the equation for maximum height, which is just v naught squared sine squared theta over 2g. And actually, I just realized I made a silly mistake. So we don't actually know what the initial velocity for the second ball is. So I'm going to give it another variable. We'll just call it s naught t, because we actually want to find what this is in terms of v naught. Okay, so then what we have to do is set this equal to v naught squared sine squared over 2g. If we plug this in, v naught sine theta g for this, we get, so let me just do it. So we have s naught v naught sine theta over g minus v naught squared sine squared theta over 2g. We can add this to both sides, and so we get s naught v naught sine theta over g is equal to v naught squared sine squared theta over g. And we can get rid of a sine theta, and we can get rid of one v naught and the g, and we get s naught is equal to v naught sine theta. And so that would be, and yeah, so that is how you would solve that problem. Okay, next problem. A wall has height h, so let's just draw the floor. Okay, let's terribly drawn. Okay, just pretend that this is level ground and that I'm actually decent at drawing, which is obviously far from reality, but whatever. So the wall has height h, and it is a distance L away. So call it L. You wish to throw a ball over the wall with a trajectory such that the ball barely clears the wall at the top of its parabolic motion. So that was a terrible parabola, but like I said, I'm not decent at drawing. Anyways, what initial speed is required? That is a good question. Okay, so what initial speed is required? Okay, so first let's look at the kinematic equations, obviously. So first let's say L is equal to V naught cosine theta times T. Then T is equal to L over V naught cosine theta. And now we can plug in this value for T for, actually let's not use L, or no, let's not use Y. Okay, H is equal to, sorry about that, okay, I lost my train of thought. H is equal to V naught sine theta T minus 1 half G T squared. But we know that H, the ball has to reach a height of H at this time when it also reaches horizontal displacement of L. So we can just plug in the time here, which is L over V naught cosine theta. And if we do that, for our first term we get L V naught sine theta over V naught cosine theta minus 1 half G L over V naught cosine theta squared. And so let's get rid of these, and this becomes tan theta, so we have L tan theta minus L squared over, L squared G over 2 V naught cosine theta. And it's asking us what initial speed is required, so we have to solve everything in terms of, or we have to find V naught in terms of everything else. So then we get L squared G over 2 V naught cosine theta is equal to L tan theta minus H, and we want V naught as the numerator, so let's just invert everything, and we have 1 over L tan theta minus H, and now let's multiply both sides by L squared G, and divide by 2, so we get L squared G over 2L tan theta minus 2H, and if we want to divide both sides by cosine theta, we get that V naught is equal to L squared G over 2L tan theta over cosine theta minus 2H over cosine theta. Actually, no, sorry. Since we're dividing by cosine theta, we'd actually multiply the denominator by cosine theta. So it's 2L sine theta minus 2H cosine theta. And yeah. Okay, so let's see what other problems are there. Okay, yes, I think that is pretty much it for this video. So this is for multi-dimensional kinematics. So the three kinematic equations here can be used in the x, y, or z dimensions, and they only work if the acceleration is constant. There's also projectile motion where there's no acceleration in the x direction, and the acceleration in the y direction is negative g. And you can also have a centripetal acceleration, which is just an acceleration from a change in direction instead of changing speed. And yeah, so that's pretty much it for this video. For our next video, we will be covering work and energy. And so I hope this video helped, and thank you for watching.